So my name is Sudip Ganguly. I'm the product manager of AutoPIPE Vessel. So today we will be learning about designing expansion joints for mainly heat exchanger applications using finite element analysis. So let's go over briefly the agenda here. Why we will use expansion joints, I will talk about that. I will cover about background of analytical methods of calculation of expansion joint. Then finite element analysis steps, which has been implemented in AutoPIPE Vessel. AutoPIPE Vessel, by the way, is a pressure vessel and heat exchanger mechanical design software. And we will be primarily talking about the newly implemented TEMA 9th finite element method for calculation of expansion joints. So this will be the first discussion. It begins with the finite element analysis steps. Then what we will do is we will do a comparison of TEMA 8th, the analytical method, versus the TEMA 9th, the finite element method. We will compare the results of the stiffness values and the stress analysis. I'll talk about mesh sensitivity study, axisymmetric element validation. Finally, I'll talk about a BEM type fixed tube sheet heat exchanger for a real world example, and analyze how we can use the expansion joint for the specific application. So why we use expansion joint in heat exchangers? The answer is very simple. Basically, in a fixed tube sheet shell and tube heat exchanger, unlike U-tubes or floating heads, the tubes are restrained in between the two fixed tube sheets which are welded onto the shell. So if you don't use expansion joints, there will be loads on the some kind of axial thrust force on the tube sheet joint, on the shell channel junctions, on the shell axial membrane stress will be increasing. So using a shell an expansion joint will obviously help in reducing such stresses. We will be discussing the thick wall type expansion joints. We are not going to discuss about thin wall bellows. And this is a brief, list of the type of expansion joint that you can design using AutoPIPE Vessel. This is a screenshot. So you can use expansion joint based on the TEMA 9th edition, which is the 2007 version of TEMA. And you can also design based on the TEMA 8th edition, which was the 1999 version. And you can also, to the right, you can see you can use expansion bellows. So those are in accordance with EJMA standards, CODAP, and EN and AD Mark letter standards. So let's go over the background of the analytical method of calculations. So a expansion joint is basically made of what you call flexible shell element, FSE. Shown here is a sketch of only one half of the expansion joint. The joint is symmetric, so if you slice it at the middle portion at the symmetric plane, this is how it will look. On the left you can see the actual picture, and on the right you can see the equivalent model for TEMA 8th. These are formed flanged and fluid type half convolution joints, and this flexible shell element, which is the half convolution, will be our main topic of analysis in the finite element method. So the earlier works include the work of Kopp and Sayre in 1952, when they proposed various analytical and experimental methods using equivalent geometry. There were certain assumptions. The outer torus replaced by extension of outer shell and annular plates, and the outer shell was not modeled. They used classical beam theory. In 1973, Wolf and Mainz, they proposed finite element based on axisymmetric analysis, but at that time, the computation speed was not that high. So finite element obviously was a very expensive proposition, so it didn't become that popular at that time. In 1984, Singh and Solar presented a very seminal work where they used the classical plate and shell solution instead of the beam theory. Then the TEMA committee in TEMA 8th in 1999, they adopted the Singh Solar method and modified the geometry to take into consideration the knuckle radii. So what was the problem with the TEMA 8? Basically, you will find, which will be one of the areas that we'll talk about, is it calculates sometimes inaccurate stresses. Sometimes it overestimates or underestimates and also the stiffness values deviate beyond a certain, if it's not close to the idealized condition. So the solution was found to be using finite element to take into consideration the complex geometry. And TEMA 9th in their 2007 edition proposed the axisymmetric FEA method. So that is what has been implemented currently in AutoPIPE Vessel software. So here is the finite element model. What was done was development of an 8-node axisymmetric isoparametric finite element engine. So there are 16 degrees of freedom, which is also called DOF, and 2 degrees of freedom per node. So you see here U1, U2 for node 1, and then it goes counterclockwise. So node 2, U3, U4 like that. And then so 1, 2, 3, 4 on the corner nodes, and the mid nodes 5, 6, 7, 8. And this is a linear static analysis, and basically this is a higher order element. So it has 8 nodes. So it will give very accurate calculation of stresses, and you can basically get very high accuracy even with less number of elements as compared to, let's say, 4-noded element. Just a little bit background on the finite element model, the theoretical part. I'm not going to get into too much details here. Just an overview. So in the finite element, basically the K matrix or the element stiffness matrix is formulated by integrating the transpose of the strain displacement transformation matrix, the B matrix, B transpose times C, the material matrix, times again B, and which is again multiplied by the determinant of the Jacobian. And that when integrated numerically over the volume, it gives you the element stiffness matrix. So the strain displacement transformation matrix is defined by such a matrix which when multiplied by U, the displacement matrix gives you the strain. So the material matrix is obtained by the formulation of the elastic modulus and nu, the Poisson ratio, and the stress strain formulations are as you see here. So in this formulation for the axisymmetric engine, you will get 4 stress tensors, which is the sigma xx or the radial stress, sigma yy or the longitudinal, sigma xy is the shear, and sigma zz, which is the hoop stress. So this hoop stress is what gives this axisymmetric element the power to calculate, because it is this is the only stress component which is what you get over and above the regular 2D element. You do not need to use 3D elements because it will be computationally much more expensive to use a 3D element for solution. And here there is no torsion or bending, so it is assumed that the system is stiffened enough against bending or torsion because of the tube bundles. So axisymmetric element works perfectly fine, and that has what has been proposed in TEMA 9th. Right, so finite element model, what happens is once you get the element stiffness computation, we use a Gauss-Legendre numerical integration of the 3rd and 4th order, and the displacement calculation is obtained by combining the element stiffnesses and making the global stiffness matrix capital K times U is equal to R, the load matrix. So when you solve this system of equations, you get the U, the unknown displacements, and from there basically through the Gauss point stress recovery, we use Gauss point, which gives much more accurate calculations of the stresses. From there on, you get the global stresses, the radial, the axial or meridional, the sigma h circular hoop stress, and the sigma xy shear stress as shown here. So this is a 3D visualization of the half convolute or the FSE that we're talking about. So this is basically the exact similar profile, the identical profile that is proposed in TEMA 9th. So here you can see the geometry which has been meshed. This is a representational mesh. So you have the vessel center line and the FSE plane of symmetry. So basically, if you have a plane of symmetry, what happens is the UY, the Y displacement is considered 0. but there can be X displacement. So the stress classification line 1, basically it's a plane, stress classification plane, but since it is axisymmetric, it is considered as line. So stress classification line SCL1. So that is the plane of symmetry where the nodes are locked in Y but allowed to move in X direction UX. So TEMA 9th also suggests that you use 8-node axisymmetric, and there are um, restrictions on the aspect ratio, which I will talk about later. What will be the ideal aspect ratio as suggested by TEMA, and the number of elements along thickness. So there will be a study that I will show you briefly on what is the ideal number of elements along thickness. So our studies also confirm with TEMA's finding. So there has to be like a total 15 stress classification lines as shown here. So 3 stress classification lines on straight portions. You see the outside cylinder, which goes from SCL1 to SCL3 with a middle plane, SCL2, and likewise 3 on the inner cylinder, which is at the top, SCL13 through SCL15 with the SCL14 in between. And then the annular plate where you find is SCL7, SCL8, and SCL9. Then each one of the torus, the knuckles, they have 3 stress classification lines, 4, 5, 6, and 10, 11, and 12. So basically, if you find the stresses at these 15 locations, you pretty much get a very accurate and good sense of the stresses due to the loading. So first, what happens is the plane of symmetry, the FSE plane, the loading is boundary condition is always same, whereas the boundary condition on the loading plane, which is the SCL15, will change. I will talk about that later. So first, it is axially loaded with a given force, and based on the displacement, we find the stiffness of the FSE. So once the step-by-step process is such that you find the global stresses that we spoke about just a few minutes ago, but what you have to do is we have to do the stress transformation. So imagine you have the knuckle, the torus, which is shown here. This X and Y are capital X and Y are the global axis. So what is needed is to transform the global stresses in the local plane, the X1 and Y1 plane. So these are the local coordinate systems, and for every SCL it will change. So from the global, the stresses are transformed into local stresses. So let's consider those are sigma XL, sigma YL, sigma HL, and sigma XYL. Okay, these are the local stresses. So once you get the local stresses, you have to perform the stress linearization from the transformed local stresses. The method of stress integration that we use is the ASME Section 8 Division 2 Part 5A, and Simpson's integration rule is applied for the integration. So there are 2 linearized stresses, the linearized membrane stresses, which is basically P by A, and it is denoted generically as sigma ij comma m, which is equal to 1 upon t. T is the thickness, and then you integrate 0 to t, the sigma ij, the stress component along the length of the SCL. And then the linearized bending stresses are also obtained by 6m over t square. Sigma ijb is 6 by t square integration 0 to t, sigma ijt by 2 minus x. This is the moment arm times dx. One thing to note here is that bending stress is only for the local hoop and meridional, and not for the radial or the parallel to the SCL plane and in plane shear. So the equivalent von Mises stress are then obtained from the linearized stresses. So the radial stresses is ignored as per the ASME 8 Division 2 Part 5A. It doesn't ask you to consider the radial stresses. Stiffness calculation, just like I mentioned, the KFSE is obtained by F axial by delta axial. So what is that F axial? F axial is the axial load that you apply at the SCL15 plane that you see here. And the finite element solution will give the delta axial, the average vertical displacement of that SCL15 plane. So you divide the force by the delta axial, and you get the KFSE, the stiffness. TEMA 8th obviously has a much more complex formula uh, where they have something called a capital K value, the stiffness multiplier, and there are a couple of functions x7, x8, q1, q2, q3, which are the functions of the FSE geometry, and A is the radius to the mid thickness of the inner cylinder, and DE is the function of elastic modulus and thickness. So with this information, what was done was that a simple case was analyzed where the outer radius of the FSE, the joint, was 652 millimeter, inner radius was 412 millimeter, the thickness was 12 millimeter, and the straight portions FB and FA was 50 millimeter. And with this fixed geometry, the knuckle radii RA and RB were varied. So you see here there were 8 cases where the inner and the outer knuckle radii were varied from 5 in short increments all the way till 110 mm. And in both cases, TEMA 9th and TEMA 8th, and the calculations are tabulated here. So the summary of this result is easily depicted, better represented in the graph to the right. So if you see in the x-axis, the knuckle radii, it actually decreases. So consider the smallest knuckle radius, 5 mm. From there, it increases to 110 mm to the left. In blue, you see the TEMA 8th values, and orange gives shows the finite element analysis obtained values, and there's an exponential curve fitting that was done. So what we find here is that for very small knuckle radii, 5, 10, up to 25 or maybe 50 mm, there is no problem. The TEMA 8 gives almost matching results with FEA. But when the knuckle radii increases beyond 75, 87, it starts deviating, and from 100 mm onwards, it almost gives a kind of like an invalid solution. As you see here, it deviates quite a lot, and this perhaps happens because of the idealization, the assumption in the TEMA 8th calculation. So when you have a very small knuckle radius, it approaches the geometry of a corner joint without the knuckle. So the knuckle radius does take into consideration the TEMA 8th method. It does take into consideration of the knuckle radius, but not as efficiently as the finite element method. So, and this is obtained very easily. The stiffness value is obtained very easily with just 3 elements. I will talk about that. So you can get this spring rate very, very fast using the TEMA 9th finite element method. In the next step, with a different geometry, the stress analysis was performed, and likewise we did both finite element method and TEMA 8th method analytical calculation comparison. And part UHX of ASME, mandatory appendix 5 of ASME section 8 div 1, they were applied, and BEM type heat exchanger was selected. Shell side design pressure, temperature and pressure 0.8 megapascal, 100 degrees C. Tube side design temperature pressure 0.1 megapascal, 150 degrees C. Step 1 in the analysis for FEA is kind of same. We calculate the stiffness, KFSE, which I covered just now. And step 2 is apply calculated end displacement from axial shell membrane stress plus the internal pressure. So what we do for the stress analysis is basically we apply a pressure load on the inner surface. As you see here, pressure load is equal to P, whatever is the shell side pressure, and displacement boundary condition is applied. You see on the SCL 15 plane, Uy is equal to dy, and this displacement, how we obtain, I will tell you. So in the first part, the TEMA 9th matches very closely the stiffness part with TEMA 8th. There's not much difference, as you see, 86,000 Newton per millimeter for TEMA 9th, and about 84.6 thousand Newton per millimeter on TEMA 8th. So it matches quite closely. So the expansion joint stiffness will become half of the FSE because it's basically 2 springs in series. So it is exactly half. So this is for one convolution. If you have multiple convolutions, it just gets reduced by that many amounts. So if there are two full convolutions, then it becomes half of this value. So in the step 2, we calculate the end displacement from the axial shell membrane stress. So you see here, this is a screenshot from the AutoPIPE Vessel tube sheet calculations. So as you know, there are 4 design loading cases and 4 operating loading cases for every load condition of the tube sheet. So for the design load cases, case 1, 2, 3, 4, there will be a shell axial membrane stress, which is sigma SM, which is the 4th column that you see. And for the operating load case as well, you will get a shell axial membrane stress. So this is the stress that is acting axially on the shell. So here in this table, for each and every design and operating load case, the shell side and tube side pressures are listed. And from the shell axial membrane stress, the 4th column, that is multiplied by the shell cross section. So that gives the axial force, F axial. And the end displacement is easy to obtain. It basically is F axial by the K FSE, the obtained stiffness value. So that gives the displacement. So if you see here design condition D2, there is the end displacement is calculated as minus 2.1 millimeter, and the applied shell side pressure is 0.8 megapascal. Likewise, O1 is the operating with 1.8 millimeter displacement, and the shell side pressure is 0. So with these two analysis was performed, and the von Mises, finally the von Mises equivalent membrane and membrane plus bending stresses were calculated at all the stress classification lines. So this is the power of the finite element, whereas instead of getting simple so hoop stress and bending stresses, circumferential stress at 1 or 2, 3 locations in the TEMA 8, you get at every stress classification line. You can individually analyze which one is which area is more stressed, and accordingly change your geometry, make modifications. So as you can clearly see, the outer knuckle and the outer knuckle to annular plate junction, the stress classification lines 6 and 7, and the whole of inner knuckle, they are overstressed. So you see the values within the box that shows you the ratio of the equivalent membrane plus bending stress over the allowable stress. So it clearly exceeds the allowable stress values. So if now we compare it with the TEMA 8th, what it doesn't linearize the stress obviously, but what it gives is the annular plate maximum meridional bending stress value, which is 219 megapascal. And we could isolate, we could recover the stress annular plate linearized meridional bending stress at the stress classification lines 7, 8, and 9. And the annular plate maximum equivalent membrane plus bending stress at stress classification line 7. You see all these values are less than that in TEMA 9, in TEMA 8th. So the stress is over predicted for TEMA 8th clearly. So this is a representation of the high stress areas along the SCLs from the TEMA 9th. So the y-axis plots the stress to the allowable ratio. So ideally, all the values should be below 1. And here you can see which stress classification lines are hitting above the value of 1. So blue line indicates the membrane, and the orange lines are membrane plus bending. So those are the two values, and also the membrane plus bending on the outer surface is defined by the gray line. So design case 2, the stress comparison was done also on the maximum circumferential membrane stress in inner cylinder and outer cylinder. So TEMA 8 predicts the stresses, circumferential membrane stresses in inner and outer cylinder as roughly 16 and 33 megapascal respectively. Whereas for the finite element, the values on the inner cylinder circumferential membrane stress, the linearized value is 29, and the maximum value of circumferential stress in inner cylinder is 53. Likewise, the linearized circumferential membrane stress in outer cylinder is 69, and the maximum value of circumferential stress in outer cylinder is 73.5. So in this case, you find that the TEMA 8 actually underpredicts the stresses. Operating condition case 1, there is no problem. Also, since this is operating condition, the allowable stress is 3 times the S value. So it is 354 megapascal because there are secondary stresses here. So you see it's PL plus PV plus Q. So it has secondary components. So it allows you to increase the allowable stress somewhat. So here there was no problem. In this case, we also did a mesh sensitivity study. So a particular geometry was chosen, and there was an iteration method where number of elements along thickness was varied. 3 elements starting from, and then varying it in increments of 3. So 3, 6, 9, 12, and 15 elements. So if you see the axisymmetric FSC spring rates, this and also the inner node displacement UX and UY for stress classification lines 3, 9, and 15 chosen randomly, you find that most of the values are not changing for any change in number of elements along thickness. So there is no significant change. So we can safely assume that if you just want to compute for stiffness, three elements is good, but we will see how many we require for stress evaluation, because in finite element the displacement comes quite accurately, but not necessarily the stress, because the stress is a derived quantity. So you may have to refine the mesh further to get the right value of stress. So for the mesh sensitivity study, what was already also done was that there were 4 points chosen on a specific stress classification line. The point number 1 being RB plus T, which is the outer surface, and point number 7 is RB, the inner surface, and then it was divided equally as RB plus T, RB plus 5T by 6, like that. In 6 equal parts it was divided. And basically, since those points are fixed, what will happen is, if you observe how the stresses vary with changing number of elements of thickness, then we can find out where exactly it actually converges. So if you can see point number 1, you get minus 209 megapascal for 3 elements, and for 6, 9, 12, 15, they're all kind of same, 206 to 207. Same for the next one, RB plus 5T, point number 2, minus 140 megapascal for 3 elements, but minus 135 and minus 134 for 6 and more elements. So 6 elements is normally what we found out as ideal for the stress evaluation. So here is a list also, a tabulation, and here is a graph where you can see the global longitudinal stress sigma YY and the hoop stress sigma ZZ. They were compared with a case where only internal pressure was applied and no axial load. And you'll find that compared to 9 elements, and the 6 elements gives very close results. The error doesn't change much, whereas for 3 elements, there's quite a bit of a error. Sometimes for the sigma YY, the longitudinal stress, you have error almost touching 3.5%, and for sigma ZZ, the hoop stress, the error is to the tune of 5.5% with 3 elements. So here also we can concur that 6 elements is not required for the accurate stress calculation. I'll quickly go over the axisymmetric element validation. This was done for a very long length of the outer cylinder and the inner cylinder, so that the stress classification lines 1 and 15, they are far away from the discontinuity, the area of discontinuity, which are the knuckle areas. So those behave as an idealized solution of a thick cylinder. So here also you find the FEA values for the linearized hoop stresses. They match very closely to the analytical method, well within 2%. So there is another validation which was done with a capped thick cylinder. So analytical solution exists for that. So it was a pressurized cylinder, capped, and this was the result for the 3 stresses, 3 normal stresses, sigma XX, sigma YY, and sigma ZZ. The dots are the calculated with finer mesh, the finite element, and the orange line represents the analytical method. It actually exactly matches with the analytical solution. This study was presented in ASME 2018 Pressure Vessel and Piping Conference. So if you go to proceedings.asmedigitalcollection.asme.org, you should be able to download this this paper for a price. So it is documented in ASME Digital Library, if you want to know more about this particular study. So now let's take a look at the BEM type heat exchanger, fixed tube sheet heat exchanger. So this is a screenshot from AutoPIPE Vessel using BEM exchanger. So this is without expansion joint. So ASME Section 8 July 2017 version was chosen as the design code, and design conditions were 0.3 megapascal for shell side, 0.2 megapascal for tube side, and 160° and 95° C respectively for shell side and tube side design temperatures. And the construction data type is BEM. The tube pitch 90° square, value 25 mm pitch, diameter 20 mm. Straight tube length has been kept as 6 meter. The segmental baffle, vertical baffles, and spacing of baffles is 300 millimeter. It was modeled with 500 tubes, and it has an impingement baffle with welded with tie rods. Now AutoPIPE Vessel automatically generates the tube sheet design conditions, but you can add or delete some of the conditions. I kept it with 2 conditions for a study case. So these 2 conditions will be evaluated for the calculation. So after running the calculations, clearly there are errors, and most of the errors are tube sheet loading related. First is the tube to tube sheet joint strength is not adequate, and then there is insufficient strength in shell and channel joint, and also the longitudinal membrane stress in the shells and tubes are exceeding. This is exactly what I was talking about at the beginning of the presentation as to what might happen if we do not use expansion joint. So this again goes back to the tube sheet design conditions tab, where you can see there are 2 conditions, tag 1 and 2, and at the bottom right you can see the screen shot from the design report of AutoPIPE Vessel. So there are 2 design, the 2 loading conditions for tube sheet, condition 1 and 2, and also there are 2 other conditions. One is for the shell side and the tube side test conditions. So total 4 conditions were analyzed. So this is the screenshot of the tube sheet design. The tube sheet design allowable loads for tube to tube sheet joint, as you can see, the LA values needs to be less than the L max. In this case, it is exceeding, particularly for the operating load case. So in AutoPIPE Vessel, in the design report, if you have an error or you have a failure, it marks it up, highlights it in red. So it is easy to interpret the report and find out what went wrong. Also the axial membrane stress in shell is exceeding. So the sigma SM values for the operating load case, if you find the absolute values are more than the SSB, the allowable stress values. So for all the load cases, actually it's failing. It is exceeding the stresses are exceeding the allowable values. The stress in the integrated shell to tube sheet joint is also not maintained, and there is insufficient strength in shell channel joint for the scenario. So with that in mind, let's stick in an expansion joint. So we will model it with an expansion joint. So we go back to that initial screenshot which I showed you. We select TEMA 9th edition. There are 2 options. Either you can do a simple spring rate design only, or a full design where you actually get to design for the stresses. So we will be doing a full stress analysis, and here the geometry is very easy to define. You basically have external height h 120 mm from where the software will calculate the length of the annular plate. Number of convolutions initially is kept as 1. Ply thickness I've mentioned 12 millimeters, same as the shell. Adjacent top adjacent cylinder length and the external length both are kept 40, as well as the knuckle radii. The inner and the outer knuckle radii is 40 mm. Down below you see there are mesh parameters. So there are two parameters here. One is the aspect ratio 2, which is as per TEMA's guideline, and elements on thickness. So basically how many elements you want to place along the thickness. The more number of elements you place, you get more accuracy. So just now what we analyzed, 6 elements are required along thickness, and these are also TEMA 9 guidelines. So TEMA 9 requires you that you have aspect ratio 2 and element on thickness is 6. So what is the aspect ratio? Basically, if you look at the right, the thickness, the width of the element is W and the height is H. So it is this H by W, which is the aspect ratio. So basically the height should not be more than twice the width, because if your aspect ratio is off and it is too long as it is broad, then the finite element method is such that it may give erroneous results. So, say for sake of accuracy, you need to maintain that proportion. So even with a single expansion joint, you have some problem. There is one tube sheet loading condition error. The tube sheet design can fail in multiple places, multiple calculations, as we saw without expansion joint case. But here we are seeing it is failing for loading condition 1. Obviously the errors have come down, but it is not 0. It's still showing insufficient designs. So the strength is not sufficient still. So insufficient strength in shell channel joint. And now there is an additional problem, which is that the stiffness is quite high because we used only one convolution. So the expansion joint stresses are also beyond the allowable values. So basically what happened here is, this is again various screenshots from the program. So on the left, we see stiffness calculation. So it is 222,790 Newton per millimeter, which is the spring rate for given convolution for the whole spring. So basically it is half of the FSE, the flexible shell element. And that value is used as the KJ value in the tube sheet calculation, which is shown on the right. So allowable loads for tube-to-tube sheet joints, these are fine, but we do see there is a problem with the stresses in the integrated shell tube sheet and the insufficient strength in shell channel joint, and these are the errors that were reported. So if you go back to the expansion joint design report, these are screenshots from there. So it explains you a little bit about the equation of the stress linearization, and it explains what the symbols mean for the various stress components, and also the acceptance criteria. On the right, you can see there are linearized stresses for 15 stress classification lines that we talked about at the beginning, and these are used. So this table is only for one load condition, loading case. So it's the design loading case 1, and there are 4 design loading case and 4 operating. So there are total 8 design plus operating loading cases, and there are 15 stress classification line per loading case. So there are essentially 120 calculations that needs to be performed for just one load condition, and there are multiple load conditions in the tube sheet calculation, right? So loading condition is what, like I mentioned, is the shell side pressure P 1.54 megapascal. It is the MAWP, and the delta is 0.235 millimeter, the calculated end displacement. And here you see in the next table it will be more clear. So this is the same calculation for operating loading case 2. So for every stress classification line, you have sigma mx, sigma my, sigma mxy, and sigma mh. These are the linearized membrane stresses. And finally, these are found once you get the linearized membrane stresses, you find the von Mises equivalent. So that is the equivalent linearized membrane stress, sigma MEQ, that 6th column. So that is the column that is checked with the allowable stress, and then there is sigma by and the sigma bh, which are the bending stresses in longitudinal and hoop direction. But these values are not checked with allowable stress. You see it is the sigma by, the bending stress, comes in orange color, which means that it's just a warning, because at the bottom you see a footnote. It says stress is not maintained, but it's also non-mandatory, because as per code you don't have to check only the bending, you check the equivalent membrane and membrane plus bending. So the membrane plus bending are checked at two locations, the inner surface and the outer surface. So sigma MB0 inner surface and sigma MBT outer surface. So those two columns, you see there is overstress, and since this is a operating load case, 3 times S is 354 megapascal, but still it's failing. So we have to do something about it. So in this case, we use double convolution. So what will happen is that the stiffness will reduce further, and hopefully it will alleviate the stress. So now, as you see, there are two convolutions. So stiffness Kj is half of 222,000 Newton per millimeter, which we got earlier. So it is halved. It is 111,390 Newton per millimeter. And here we see a clean report for the tube sheet design. No error on tube sheet. And also, if we compare, we got with one convolution, the stresses exceeded, the design failed, right, for operating loading case 1. But with two convolutions, all the stresses are within permissible limits. And the same goes for the operating loading case 2, where the stresses exceeded and the design failed. But with two convolutions, the stress is within limit, the design passes. So this is an example. It is not necessarily that your expansion joint will necessarily pass if you just add one more convolution, or just by adding convolution the design may pass. So you have to play around with the geometry, maybe add convolution to see what makes the expansion joint suitable to make it, to keep the stresses within allowable. So as conclusion, what we discussed was that we had a mathematical model of an axisymmetric finite element program that we discussed, and also some studies on the validation was presented. So what is basically the takeaway? What is the major advantage of using FEA? So it is basically the analysis accuracy, and complex geometries like expansion joint, they particularly lend themselves very well to FEA kind finite element analysis. And it produces accurate results of stresses and displacements at every single location. So you can analyze at various different points along the geometry of the expansion joint, not just 1 or 2 or maybe 3 sections. The older analytical methods worked earlier. They worked within certain limitations, as we discussed, and sometimes it can produce inaccurate results. It can over or under predict. That is because of the oversimplified geometry, because it's not easy to find analytical solution of very complex geometry. So there were some assumptions which we talked about, and because of that oversimplified geometry, it could have produced over or under stresses, prediction of stresses. And we talked about mesh sensitivity, 3 elements, normally good for thickness, for displacements calculation, or stiffness calculation, and for stresses, 6 elements are necessary. And then we finally talked about the practicality of the use of finite element based on the TEMA 9th edition for the thick wall expansion joint for heat exchangers. So there is a product data sheet that is available for AutoPIPE Vessel. You can go to this site, www.bentley.com. And with that, I would like to thank you all, and I will take any question that you may have.
Thanks, Sudip. Very interesting. I've got a couple of questions for you. First one, what was the stress linearization method based upon?
It was the ASME Section 8, Division 2, Part 5A. That was used for the stress linearization.
Okay, and why choose axisymmetric element rather than a 3D solid element?
Right. So 3D solid element is an overkill. So axisymmetric element is basically similar to the 2D element, except for that it gives you one more additional stress, the hoop stress, which you don't get from 2D. And the amount of complexity that you will add will be unnecessary by adding a 3D element. So the computation time, and just like I showed you, for every loading case, you have so many different design and operating cases, and you have 15 stress classification lines. So it would have taken much more time and effort to calculate by 3D. And basically, since this is axisymmetric problem, since there is no assumed to be no bending or torsional loads, so axisymmetric works fine in this kind of application. That's what we agree with TEMA 9.
Okay, that's great. Thanks. Are there any more questions from attendees? I've got another question here. Was this developed completely by Bentley, or was this extracted from third party, or is it an in-house development?
No, this is fully 100% developed by Bentley Systems, starting from the axisymmetric engine to stress linearization routine to the reporting. Everything was developed in-house. It doesn't depend on any third-party component.
Okay, thanks. Could the analysis be done with the 4-noded element versus 8-node? What's the benefit of the 8-node?
So 8-node is a higher order element. You can potentially do with 4. First of all, we are following TEMA 9th guidelines. So TEMA 9th requires you to do perform the analysis with 8-node elements, axisymmetric element. You could do with 4 nodes, but since those are lower order elements, you would have to mesh it much more finely, like much more number of elements along thickness. Here you require less number of elements along thickness because there are center nodes. There are nodes in between the two corner nodes. So total four on the center and 4 on the corners. So total 8 node elements, higher order elements, so more accuracy. So yes, you can probably use 4 nodes, but that would be more efficient. You would have to use much more number of elements to get the same result, same level of accuracy.
Okay, that's clear. Thanks.